So when we talk about the idea of ionic bonding, well, we need to understand a few things. Number one, we need to understand ions, which we have been going over. But we also need to understand who is ionically bonding here. And ionic bonding only occurs between metals and nonmetals on the periodic table. So when we're actually talking about that, okay, we need to actually go back to the periodic table just for a little reminder as to what a metal is versus a nonmetal. So if we remember correctly, we've got this staircase here on the periodic table. And that staircase is what's going to differentiate what a metal is versus a nonmetal. So anything to the left here is going to be a metal. Okay, and there's only one exception to that, and that's hydrogen. Hydrogen is over here. You'll notice how hydrogen is not actually attached to lithium like everything else is attached to one another on the periodic table. And that's because hydrogen here is actually a nonmetal. All of the nonmetals are on the right side of the staircase, including hydrogen. Hydrogen's only placed where it is because it has one valence electron. It is the exception to that rule. So now that we kind of have that memory or that reminder of metals versus nonmetals, it's going to be really handy to have a periodic table when we're doing bonding, because as we move through bonding, we're going to be looking at two types of bonding. We're going to be looking first at ionic, and then at something called covalent bonding. And in order to be able to identify whether it's ionic or covalent, you need to know who the players are. You need to know what kind of atoms are involved in the bonding, because automatically it will tell you whether it's an ionic bond or a covalent bond. And that'll allow you to explain or understand what's happening. So when we talk about ionic bonding, we're talking about metals, okay, bonding to nonmetals. So that has to do with the actual staircase, all right? We don't really care about metalloids here. We're actually looking at metals versus nonmetals. So it really is going to depend where you are on the staircase. And the general rule here is that metals will be the electron givers. Because if we go back again to that periodic table, okay, we see that all of these guys here, okay, all of these columns or groups are going to have set valences. So that everything in group 1 over here is going to have 1 electron to give away. Everything in group 2 will have 2 electrons to give away, because it's easier to give away that number than to collect a total of 8. Okay? Group 13 will give 3 electrons away, and then we're in the middle territory with group 14. They've got 4 electrons, so they're either going to be givers or takers. It depends who they're bonding with. Then we get into taker territory, because anything in 15 has 5 electrons, it will need 3. 16 has 6 electrons, it will need 2. 17 has 7 electrons, and it will need 1 to fill its valence shell. This group over here doesn't need any. The noble gases or inert gases in that group, they don't really bond with anything else because they don't need to. So when we're looking at ionic bonding, the idea of metals being givers and nonmetals being takers is going to help us remember who's going to be doing what. So if we go back here, let's have a look at these 2 examples, okay? We're going to be using Lewis notation to show ionic bonding, because we're looking at who is doing the giving and the taking of valence electrons. We're only dealing with valence electrons here, so it doesn't really make sense to draw the big Bohr-Rutherford model. So I'm going to start off with my sodium, and sodium has one valence electron. I'm then going to draw, and I like to use a different color and a different symbol for my electrons because I find that I'm able to visualize where all the electrons come from a little bit better. So my chlorine, if you look at the periodic table, you'll notice that chlorine is actually period 3, group 17. Therefore, it has 7 valence electrons. So I'm going to draw that in. 1, 2, 3, 4, 5, 6, 7. Now I'm hoping that as you look at these two atoms, you'll see that these are two pieces to a puzzle that perfectly fit together. Chlorine has 7 valence electrons, therefore it is missing 1. Sodium has 1 valence electron. So what's going to end up happening here is sodium is going to give this electron to chlorine. Sodium will then fall back on its second valence shell, or its second electron shell, which is full. And that 1 electron being given to chlorine will fill chlorine's third shell, or its valence shell. So what we end up seeing here is that this atom will actually move into, okay, it'll move into right next to, and they'll be bonded together. So what this actually looks like in chemical speak, okay, is an Na bound to a Cl. Okay, they form this bond or this bridge. And if you remember, we've actually seen images like this before. Way back when, we talked about the fact that these lines signify a bond, right? And that means that there's 2 valence electrons there being used to create that bond. So if I go back here, I see that this is a nice 1-to-1 ratio. Okay, 1 atom of sodium was able to complete or form a bond with 1 atom of chlorine. So now we're going to look at calcium oxide, and we're going to look at what happens when it's more than just 1 electron. Because if we look at this, calcium, okay, if I actually draw calcium, calcium is in group 2, which means it has 2 valence electrons. Now, if I look at oxygen, oxygen is going to be in group 16, which means oxygen is going to have 6 valence electrons. 1, 2, 4, 5, 6. Now, again, this is a 1-to-1 ratio. Okay? You should be able to see here fairly clearly that the 2 valence electrons from calcium will complete that valence shell for oxygen quite nicely. Okay, so again, right here, these 2 guys are going to move over here like this. So we're actually going to see this molecule form when the calcium actually moves over. And that's going to create this bond. Ca is going to be bound to O like this. Okay? And that's where we get these actual chemical formulas. That's what that means. So we asked the question, okay, while we were doing this, these are 1-to-1 ratios. This is as simple as it gets. Life is not always that simple, and nor are chemical formulas, nor are molecules. Okay, molecules and compounds don't always follow that 1-to-1 ratio. So we're going to use an example here with potassium and sulfur, okay? So potassium is the letter K, and this is where we're going to see that it is not a 1-to-1 ratio. So potassium between K and between S. So the reason I've chosen this, I like to put my metals in one color and my non-metals in another color because it helps me kind of make sure that I understand who the giver is and who the taker is. So I'm going to draw potassium here. If you look on your periodic table, you will see that potassium has one valence electron. It is just below sodium, and it is in the same group, therefore it has the same valence shell. Okay, and if we look at sulfur, we're going to see that sulfur is also in group 16. So sulfur has 6 valence electrons. S is going to have 6. So I'm going to draw 1, 2, 3, 4, 5, and 6. So when we see this, we notice that it is not a 1-to-1 ratio here, in the sense that if this potassium gives its electron over to sulfur here, there's still a gaping hole right here. And that is not going to create a stable molecule. This, as such, cannot work. Okay, it will not form. So what we need to do is we need to look at our players. We need to look at the atoms that are available to us, because those are the only atoms we can add more of. Okay, I cannot add a hydrogen. I cannot add a chlorine. I can't add anything else. I have to stick with either potassium or sulfur. So I am missing 1 electron. Now, if you look at these two, which one has 1 electron? I'm hoping you're going to come up with potassium here. So what we can do is we can actually draw in or add another potassium to the mix here. And in so doing, okay, I'm going to put it on this side. And in so doing, you're going to see that that potassium is then going to give its electron over to this missing side. Okay? So these guys here are going to end up, okay? So we're going to get rid of this and this. We're going to get rid of this and this. And we're going to move them in. So what ends up happening is this potassium comes in here. And this potassium is going to come in over here. And you're going to see that both potassiums give away their 1 valence electron. So they fall back on a full shell. And sulfur now has a full outermost shell. Everyone is full. Everyone is stable. Okay, this forms a stable bond. The overall bond is neutral between all of them, right? But individual atoms here are no longer neutral, right? So we end up writing this. We count out, and we always go metal first, followed by non-metal. Okay, so it's always going to be metal, then non-metal. So if I want to write the chemical formula here, I end up with how many Ks? Count them out. You've got 2 Ks, so we get a small subscript 2. And then you're going to add however many nonmetals you have. In this case, we only have 1 S. So potassium sulfide is actually K2S. And that shows you a non-1-to-1 ratio here. Okay? So what I want you to try and do for homework is I want you to draw out the ionic bonds for the 3 following examples. And you're going to notice that the examples are both in chemical formula and the words of the atoms, because there's different ways of giving you this information, and you need to know how to process it. So the first example that I want you to try is going to be magnesium bromide. Okay, so that's MgBr2. I want you to try and draw this out. Okay? And then I'm going to get you to actually do something different with the second one. I'm only going to give you the elements, and you're going to have to figure out how many of each are going to be needed, okay, in order to make the bond. So we're going to go with aluminum, phosphide. Okay, so aluminum and phosphorus. Okay, those are the 2 that I want you to bond together. And then the last one, which is going to be a trickier one, We're going to go with aluminum again, but there's going to be 2 aluminums and 3 oxygens. And I want to see how you put those together. Okay? So this video will be posted. And as always, reach out if you need help.